Okay, cool. So yeah, so I'm Sam, and I'm going to be talking about the fitters that we have in Rat, and then also like how you can add your own if you're trying to make a fitter for ratpac-two or a private experiment repo. So oh, and also I have like code on some of these slides, and I'm realizing it might be hard for people to see. So I just want to remind people that I've already, or Tanner's already uploaded these slides to the Google Drive, and so if you want to follow along on your own screen, you can just download the slides and look at them there. So just a quick overview. I'm first going to just talk about what fitters are. It's kind of a semantic term that kind of has no meaning, but it's the term I'm using. So I'll kind of explain what I mean by a fitter. And then I'll talk about some important classes that you have to understand to know how to implement your own fitter, how the fitters work. And then I'll talk about how the fitters are just basically processors. So it ties into a lot of what Tanner talked about yesterday. I'll go over some examples for both quad fit and then the fitter input handler. And then we'll talk about how you can register your own fitter and add it to ratpac or your own private experiment. And then I'll say a couple words about minimizers and then the fitters that we have in ratpac-two. So what fitters are, well, at least in the context of ratpac-two, fitters are just like special processors that tell us something about the event that we observed in our detector. So, usually we want to reconstruct certain quantities from events in our detector, including energy, direction, position, or you can do other things like a likelihood test. And so, ratpac-two enables us to kind of run these fitters on events that we see in our detector. So every fitter is implemented as a processor. And so processor base class is any processor that you want to call in the event loop has to inherit the processor base class. So the code here on the right just shows all the different methods and member variables in the processor base class. And so I know Tanner covered this in depth yesterday. And so I'll talk more about this processor base class kind of in the context of adding your own fitter. And then don't panic about all the code on this slide. You don't need to understand basically any of it, but the fitter input handler is like kind of another important class in the context of fitters. And I'll have an example of how you can use the fitter input handler if you're trying to write your own fitter. But basically the fitter input handler is a universal interface for users to kind of access PMT information in their own fitting methods. And so it kind of just, it might look complicated here, but it makes it easier for you to access the information you want to access to when you're writing your own fitters. So I'll talk about this more later in the example I have. So again, fitters are just processors in Rat. And so they can overload any of the processor methods from the processor base class. But essentially, since fitters are trying to look at an event in our detector and reconstruct some quantity we're interested in, you really should most of the time you should really overload the event method, right, instead of the DS event method. And so in the event method, you have access to kind of all the information in the EV branch, which includes PMT information. That's usually what you're most interested in. And so there are a couple other methods that are good to overload sometimes as well. So like begin of run gets ran at the beginning of every run you're processing in Rat. So typically that gets ran every time you run Rat, and begin of run can be really useful for kind of configuring your fitter depending on like the material you're fitting in or other options that the user might supply. And so I'll kind of go more in depth about what you could do in each of these methods now. And so when you first start writing your own fitter, what you would do is you would initialize, or you would write the constructor for the fitter that you're writing. So I just have kind of an example here called fitproc. And so when you write the constructor, you need to both initialize, the processor that you're inheriting from the processor class. And so you're initializing the instance of the processor class. And the only argument there is, the name of the fitter you're writing. So for quad, this is called fit quad or whatever, however you want to identify your fitter. And then also you have to initialize the input handler that helps you, access the PMT information in other methods. And begin of run, again, this is a good time to kind of configure your fitter if you have any configuration that you have to do kind of at the beginning of the simulations. So essentially in begin of run, you get access to the database, the Rat database. And if you need to load certain parameters for your fitter, you can find the table that contains information for your fitter. So usually you just call it fit _ the name of your fit. And then you can kind of retrieve different variables that you want to use, like you see here. And then the set, type arguments are useful for kind of allowing users to on the fly override what some of these parameters in the fitter are. So I think this will make more sense once we start talking about quad fitter. But for example, if you want to test, your fitter with different indexes of refraction in your material to see like how that affects the reconstruction result, you can kind of, if your fitter has a parameter that takes in the speed of light in that material, like quad fitter has that, you can kind of override the speed of light in the material using these set template type methods, and that'll kind of allow you to do it. You can actually, in theory, run like multiple processors of the same type with different values as you run events. So, okay, and then so when you're kind of loading these parameters in your fitter, you have to be able to kind of throw errors if you can't find the parameter, or if a user tries to set a parameter that you don't know how to set. And so, for example, if they give you a parameter name that you don't iterate over in your if else if statements, you have to throw this param unknown error. And so these are all defined in the processor base class, and so you have access to them in your fitter methods. And so essentially, you want to throw the param error if something happens while you're trying to set a parameter, and then the param unknown exception should be thrown whenever that parameter is not known to the processor. And then you can use invalid when someone tries to set a negative value for some kind of parameter that should always be positive or something like that. Okay, and then in the event method, again, this is where you overload like the actual fitting algorithm that you want to use. And so so the event method gives you access to both the DS and the EV data structures. And basically, this is just where you run whatever algorithm you're going to run on the event. And then if the fit converge and all values valid, you should return this OK enum variable. And then if it fails, you should return fail. And then if you really want to abort processing for the rest of the event, you can return the abort. But typically, you just need to return fail if the fitter doesn't work for some reason. And then some fitters also overload this end of run method that gets called kind of like as the simulation is cleaning up after the run is finished running. And so really in modern C++, I don't see much use for this in terms of fitters. Sometimes people used it when they had to like instantiate pointers. But nowadays you really shouldn't use pointers in modern C++. You can use smart pointers, and those get erased automatically by C++ now. And so like this could be useful if like you're writing your own fitter and you want to make sure it's working. And so after every simulation, you want to print like the mean of a reconstructed distribution. You could put that in here, but in production code, I don't really see a reason why you would do that. Okay, so I think if you're not really a developer, that might have all been really in depth, but I think we're going to look at an example now of like how quad fit works. And hopefully this is kind of more illuminating for people to see how the fitters actually work. So the way the quad fitter works is it selects groups of 4 PMTs. And if you select 4 PMTs and you're trying to reconstruct a position at a time, you have you have a set of 4 equations with 4 unknowns. And so you can actually solve exactly and analytically for the position that light must have been emitted from. And so if you repeat this process many times with different sets of PMTs in your event, you actually get like this cloud of points. And if you take the median of that cloud, you can kind of get a robust metric of like where the event in the detector must have happened. And so it's a really simple fitter. Well, simple is a relative term, but compared to like likelihood fits or something like that, it's pretty simple. And so here's some examples of what the quad fit code looks like in ratpac-two. And so if people want to write their own fitters, I heavily recommend looking at some of the other fitter implementations and basically just copying the code and then changing it for what you need. So that's what I did. So I wrote the quad fit implementation for ratpac-two. And I basically just looked at the centroid fit and copied stuff over and then changed it for what I needed to do. So I encourage that for anybody who wants to write their own fitter. But essentially, we see the same thing I talked about before with the constructor. You just basically have to define the processor name, and then you have to kind of, if you need the input handler, which again I'll talk about a little bit later, you have to instantiate it here as well. And then in begin of run, I set the run and I get the PMT info. I cache both those things so I can access them later in the event method. And then I initialize a pointer to the DB so I can access the table for the quad fitter. And then there's a couple parameters that I have to that the user has to supply to me, so I know how to run the quad fitter. And so that includes like the number of points you want to generate points for in the quad cloud, and then also the maximum number of points you want to generate. And then you also need a table cutoff, which is just kind of some internal implementation thing I won't talk about too much. And then also, like I said, quad needs a light speed to know how fast the photons are going in the material. And so this is a good example of where if someone tries to set a light speed less than 0 or faster than the speed of light, you can throw an error here because it doesn't really make sense to have the speed of light outside of those values. And then also quad has a max radius. So if you get points outside of this radius, you should throw them out. And so again, this is something that the user should specify for the geometry they're using. And so users can do that by overriding the values in the ratdb table. Yeah, go ahead.
Why are we setting the speed of light? Is that because of the speed of light in the medium?
Yeah, exactly. Yeah. Because you when you solve the system of equations, you have to solve for like how far that photon traveled to get to that point and how long that took. And so you need the speed of light to compute that. Yeah. So if you're in water or scintillator, that value changes, and we expect the user to kind of specify that value. Okay, and then again, like I said, we have this setD command also, and so you can use this to set both the light speed or the max radius. And so the difference between setting these values in begin of run and setting these values using like the setD methods is kind of nuanced. Basically, if you want to use like the /rat proc set commands, you have to implement this setD method to allow users to kind of set it on the fly. But if people update the values in the database itself, that'll get handled by begin of run. And so that's kind of a nuanced difference. I think for most cases, it really doesn't matter. You probably really only need to implement this in begin of run, but it's kind of like the rat paradigm to have both. So if you're writing this to get put into ratpac-two, we'll probably ask you to have kind of both ways of setting these values. Okay, and then this is the actual quad fitting algorithm. So this is what's ran in the event method of the processor. And so basically all this code is doing is it just loads the event into the input handler, which I'll talk about a little bit later again. And then it just caches some PMT info. And then kind of an important thing that you should always do when you're implementing a fitter is you want to make sure the fitter actually can be ran. It's like for quad, you need at least 4 hits, because if you have 3, the system of equations actually can't be solved. Yeah.
What's the difference between using log die in begin of run versus the param unknown?
Yeah.
In the setD. Is it or param invalid? Is it still like kill macro?
That's a good question. Oh, so yeah, so these probably all should be log die. I think that's a good question.
Log die guarantees that it dies, but the error can be caught by something upstream.
Yeah.
Okay, so it could just go back to like the default values, right?
So whoever calls setD could say catch this parent of something else.
Yeah. I guess if we were doing code review, like which is the right thing to do? Probably log die, because it doesn't make sense to have a negative speed of light. So I think this probably should just die, because you want the process, you want the program to end, right? It makes no sense at that point. Yeah, good catch. That's something I missed. Okay. Yeah, so this is just the main like quad fitting loop. And so this is where you would put the algorithm that you're using to actually fit, the data. And so again, I just cache some PMT info that I need to use later, and I make sure the fitter can be ran. And yeah, so that's an important point. Like if your fitter needs like some number of hits or it needs like some like a seed from another fitter, you should check that information before you actually run the fitter, and then return like invalid fit information if you can't actually run the fitter. And then after the kind of main fitting algorithm is run, you have to like check and make sure that the fitting algorithm actually converged or worked correctly. And that will inform you whether or not you want to if you want to say that the fit result is valid. And then you actually have to add the fit result to the fit result data structure, which I'll talk about in a second also. And then you want to return the processor status. So, if the processor fit and everything went fine, you return the okay. And if, something went wrong, you return the fail, right? Okay. So like I said, you have to append the results of the fitter to this DS fit result class. And so this class basically just specifies the fitted quantities that you're enabling for this fitter. So like a fitter can only fit position, or it could only fit time, or it could fit position, time, and energy, right? And so you kind of have to specify which things your fitter wants to fit in this DS fit result class. And so in your fitter event loop, or in your fitter event method, you should create an instance of this class and populate it with fit results. And then one really nice thing about ratpac-two is when you create this fit result, when you instantiate this fit result object and populate it with fit results, it actually automatically gets appended or added to like the out root or out in tuple out files if you're generating those. And just to kind of make this a little bit more concrete, you can see how I do this in the quad fitter. You guys see my mouse? Okay, good, nice. You can see how I do this in the quad fitter code. So basically, you just instantiate a pointer to this fit result right here. I think you have to use a pointer here because that's how ratpac-two keeps track of the fit results. I think that's why I did that. So this is one place where you have to use a pointer, but in general, try to always avoid using nudes. But so you instantiate this fit result. And then, initially you want to say that the validity for the things you're fitting for is false because you don't know if it actually is going to succeed or not. And you want to set the validity for things that you're not fitting for to false also because your fitter's not going to fit those things. So quad fitter only fits position and time. So I say that, the energy validity and the direction validity are both false. And then I also set the position and time results to some nonsense values because, I'm not actually fitting, or I haven't actually fit for those values yet. And then if I can't actually fit the event because I don't have enough hits, I set the validity for both time and position to false. I add the fit result to the event. So that's like saying that, I tried to fit this event and I'm adding the result there. And then I have to return that processor fail, right? So that's in case I can't fit the event. And then if the fitter actually succeeds, what you do is kind of here at the bottom where you actually set the fit position to, the fit value that your algorithm returned. You set the time, and you should also set both you should set the validity for for all the things you're fitting to true also, which gets done in quad. It's just not in the screenshot. And then you have to add that fit result to the event, right? And then you return the processor. Okay, that's kind of how that all works. That makes sense. Okay, and then so I'm going to talk about the fitter input handler for a second now. So again, this is kind of like an interface for fitters to access PMT information and other fit results. So you can kind of see like some of the methods in the fitter input handler are like get seed position. So if you want to seed your fit, you can get a seed from like another fitter or something like that. Or you can like find fit results from other fitters. Another really useful thing is like get time and get times. And so this is like if you're iterating over all the PMTs, we have methods to like extract hit times from waveforms in ratpac-two. And so, you don't want to have to fit for times in your waveforms every time you use a fitter, right? So essentially what you do is you run a waveform processor that extracts hit times from the PMT pulses. And then the fitter input handler makes it easy for downstream fitters to just get times from those waveform processors. So essentially you just say, I want to get a time for this PMT and it just feeds you the time that the waveform processor fit before. So that's basically why you would use the fitter input handler. It's just to kind of access these pre-processed times that you do kind of earlier on in the event loop. And so just to reiterate how this works in quad fitter, like I said, in the constructor, you initialize this input handler. And then in the event loop, you have to actually register that event in the fitter input handler so the input handler can kind of access all the correct information for that event. So that's what's happening here in this register event line. And then as I iterate through all the PMTs, or I can use the fitter input handler to kind of iterate through all the PMTs. And then I use the fitter input handler again to access the hit time for each of the PMTs. And so like here I'm using get time. And so that just returns the earliest time that PMT was hit in case it was hit multiple times. But if your waveform processing is advanced, then it returns multiple times. If a PMT was hit multiple times, you can also use get times here and it'll return like all the times that PMT was hit. So But so this just makes it really easy for you to access that PMT information, depending on, you know, how you're actually doing the waveform processing. So this kind of all happens automatically. Yeah. Okay. And then after you've written your fitter, Tanner kind of mentioned this yesterday, about how you actually have to like append a processor, for ratpac-two to know how to use that processor or where to find that processor. And so the same thing has to happen for fitters, since fitters are just processors. So you can see here, this is where all the fitters are appended in ratpac-two right now. And so if you wrote your own processor, you would basically just copy one of these lines and then just change the template argument here to the fitter, you know, to the name of your fitter. And then you also have to update the CMake list text file to also include the code that you wrote. So that way, you know, ratpac-two knows to compile your code as well. And then I just wanted to briefly talk about minimization, since minimization is often useful for fitter methods. So, you know, if you're using a maximal likelihood method or some kind of goodness of fit metric to fit your events, you need to use a minimizer or a maximizer. And so if you do need to do that in your fitter, there are examples in ratpac-two that use minimization. And so basically what you have to do is you have to inherit the minimizable class. And all that does when you inherit the minimizable class is it requires you to implement a operator method. So that basically just means that you can call, when you call the fitter, it like does something, it returns some kind of value that the minimizer can try and minimize. And so in ratpac-two, we have some kind of built-in ways for you to do the minimization. You can use simulated annealing, which we have in ratpac-two. There's an implementation. You can also use minwe through root, which is another good option. And then there's also, you know, you can write your own custom implementation if you want to. And so, you know, the root minwe minimizers are all documented through root. And then the simulated annealing class has documentation on the ratpac-two docs. So I won't go into it here, but if you're interested in learning how to use the simulated annealing minimizer, that's where you can find more information. And then I just wanted to say some words about fitters that we have included in ratpac-two. So if all the implementing a fitter was something you're not interested in doing, you just want to know how to use fitters, this is the slide for you. So I would, you know, this is where you could start paying attention, I guess. So I talked a lot about the quad fitter. So that's one of the fitters that's included in ratpac-two. And this fitter basically just fits position and time based on the hit PMTs you have. There's also this fit path processor. And so this is, I think it's colloquially referred to as the path fitter, but this basically fits position, time, and direction based on the PMT hit times and the angles of those hit PMTs relative to the reconstructed position. And so one thing about this fitter, if you want to use it, you have to actually feed PDFs into the fitter for it to know how to fit the data you're looking at, because it's a likelihood-based fitter. So that's one kind of thing you have to keep in mind if you want to use this fitter. There's also the fit tensor or the tensor fitter. Oops. So this fitter, this is actually a machine learning based position, time, and direction fitter. And so again, you kind of have to train your own model and feed it into ratpac-two if you want to use this fitter, but it's here. And basically once you do the training and export the model, you can kind of use it. It should be pretty easy to use, is my understanding. And then there's a centroid fitter, which doesn't require any kind of training or anything like that, any kind of coordination. And this is kind of a charge-based position fitter. So it just takes like a weighted charge average of all the hit PMTs and then fits a position based on that. And then there's also the fit direction center processor. And this fits the event direction by just taking all the hit PMTs in your event, and it just takes the average vector of all those hit PMTs and says that's the direction. So pretty rudimentary. And again, because this one's simple, it doesn't require you to create a PDF or anything like that. So, so if you're writing like your own experiment and you just want to be able to reconstruct direct or positions in your experiment, I recommend using quad if you're using kind of something that's not super bright, like water or some low light yield scintillator. And then if you're using like a really bright scintillator, where all the PMTs get hit multiple times, you'd probably want to use the centroid fitter, because that'll include the charge information in your fitter. And then if you're looking at fitting direction, the easiest fitter to use is this direction center processor that just kind of fits the direction using the PMT positions. And then if you want to kind of use more advanced fitters, you can try and coordinate, this path fitter, or the tensor fitter, if you're interested in that, or implement your own fitter if you're working on another experiment. Okay, so just a quick summary now. Like I said, fitters in ratpac-2 are implemented as processors, and so they inherit all their methods from the processor class. When you're writing a fitter, you almost always want to kind of do your fitting algorithm in the event method because that's the actual information that you'll see in your detector. The begin of run and set type functions are useful for configuration, like we talked about. And then I just want to highlight again that ratpac-2 does supply methods for optimizing functions, and it also comes with a selection of fitters pre-installed. And so if you're just trying to see how well Reconstruction would do and some detector really quickly, you can do that in ratpac-2, which is pretty nice. So that's all. Any questions?
I might have a pointed question I should probably ask you offline, but in the quad fitter code example,
Yeah.
you had 4 sorts like in a row.
Yeah.
What does that do? Because I would assume that you could sort, say, as a function of time, or so if you sort both, like it's a very pointed question, so I can maybe ask you a bit later, like that piece over there.
Yeah, so you sort the you have to sort.
Let me bug you a bit later.
Yeah, so the reason you do that is because you want to take the median of the quad cloud in each of the dimensions.
Okay,
And so you have to sort because then you look at the middle entry.
and it's gonna create. I see that makes sense.
That's
Okay.
that's the idea.
Okay, thank you.
Yeah, no problem.
Again, very nitpicky.
Yeah. Sorry. So if this talk was a little too in depth, feel free to come up and talk to me about how to add fitters. I think I'm the one that has the most experience adding fitters, so I'm happy to discuss or share my slides or any other information I have. But really the takeaway for users is that, these are the fitters that you can use, and you just kind of instantiate them just like processors in your macro, and you can use them, to fit events and whatever geometry you end up using in ratpac-2. Oh yeah.
Talk a little bit about if you run multiple fitters, how would that information be presented in couples?
Yeah, multiple different fitters. Yeah. So my understanding is that the output processors, which Tony will talk about in a second. So I think you all have seen now that when you run rat, you can have it output like a root file or an untuple file. So when you add the fit result of your fitter to the event object, ratpac-2 will automatically kind of keep track of your fit result. And then in the untuple, what it does is it basically adds a branch that is like if you're doing position fitting, it says like X position and then underscore the name of your fitter. And so that's how it keeps track of it. So like if you're fitting quad in the untuple, you'll get a bunch of branches that say like X position underscore quad fitter, Y position underscore quad fitter, Z and T. So that's how it does it. And then if you run another fitter, like the path fitter, it'll also append like X position underscore path fitter or whatever. So that's all happened. That all is kept track of naturally, which is really nice as you run more and more fitters.
You said you can get the results of other fitters for calculations in a fitter.
Yeah.
If you're running multiple fitters and then one of them uses that function, is it gonna double run it or will it get the results?
Yeah, so those fitters, so James actually wrote the fitter input handler, so he can correct me if I'm wrong, but my understanding is that, as you load the event in the fitter input handler, which you do at like the beginning of the event loop, or the event method of your fitter, it accesses the fit results that are already cached in the event, right? So it won't run it twice. It just accesses the fit that's already there. But that means if you want to use quad fit to see like your tensor fitter, you need to run the quad fit first because it has to have that fit result already there, right? So you kind of have to be careful about that in the macro. But yeah, that's all handled, it doesn't make it run it twice. Yeah. Okay. Good.